All right, we're gonna discuss shear strength in the typically AISC specification, and we're going to focus mainly on wide flange, hot rolled wide flange shapes. We'll discuss briefly built up plate girders, and they're just a whole different set of conditions that really need to be investigated if you're going to if you land in the bridge design world. Okay, so we'll take a little scratch at the surface here. Okay, so again, some review from 243, right? For calculating Q and shear stress. Okay, shear stress being VQ over IB. Okay, so you should remember that, I'm hoping. Then we'll talk about C sub V and how it varies, but again, it'll get a little bit simplified, but it's still going to relate to H over T ratios. Okay, so H over T ratios. Sorry, I'm changing my pen color. If I can find it. All right, so yeah, there, H over T ratios. Then V sub n becomes actually pretty straightforward for us. V sub n is going to be 0.6 Fy times D times TW. And again, this should be familiar. Area of the web. This is the way we talked about it in strength of materials also. Okay. So general provisions, chapter G1 of the AISC specification is really the part that we want to, or the whole chapter there. G1 general provisions, and then G2 I-shaped members and channels. Okay, and then we'll come back later on in a different part of the lecture series and talk about beams with web openings. Okay, so G1 out of your steel manual looks like this. Again, there are 7 different sections. Okay, the first in general, phi values 0.9 and 1.67, similar as they were before. And then it just tells you that the nominal strength is calculated through G1 through G7. Okay, so again, we're going to focus on G2, I-shaped members and channels, but there's a series of others in there that, you really, if you get into this area, you're going to have to become more familiar with. So notice here, shear strength of webs without tension field action. Okay, tension field action is a phenomenon with bigger or deeper plate girders, where what happens as you start to see shear stress developing. Okay, if you remember these little discussions, if I cut a section through that element, I can start to get tension. Okay, so you can start to see tension develop on in webs. Okay, but again, we're going to avoid that for now. So we see this equation here. V sub n is 0.6 Fy AW. Okay, it's times C sub V1. Okay, so hopefully we end up with the C sub V1 of 1.0 is where we should end up. Okay, so we'll talk about that momentarily. All right, so again, we are just dabbling in the surface here. Hopefully this is familiar to you. Okay, this example we worked through in strength of materials. Again, I would encourage you, if you don't remember how to calculate Q, right? Q is just a summation of the AI, YI from the neutral axis. Okay, and this is referenced from neutral axis. Okay, so if I wanted to calculate the Q above point B, right, I'd take this entire area, right, the entire area, all right, I'd take this entire area here if I wanted to calculate Q right here. Oops. Okay, if I wanted to calculate Q at this location here, I'd have to take this entire area of the flange times the distance from its centroid down to here. That's bar Y bar I. Okay. So again, it's just a summation of those values to get Q. Again, just remind you, take a look at your strength and materials notes if that's not in the front of your brain. Okay. All right. So that VQ over I equation, right? Shear stress VQ over I B. Okay. B being the width. Sometimes you'll see X I VQ over, or I'm sorry, T VQ over IT. Okay, it's really just the width of the shape at the point of calculating shear stress. Okay, we've used that equation and we'll continue to use it or base our discussion on it, but you need to be aware of the limitations. Okay, it does not apply well to shapes like this. Okay, it applies well to shapes that have a narrow width. Okay, and again, the D being this. Okay, so if I look at a D over B ratio, okay, D being 10, B being 2, a D over B of 5, okay, it is good. Okay, research showed in the 60s with D over B of 3, right, there with the D over B of 2, there was a 3% error in the shear stress. Okay, if we go again D over B here, which is 10 over 5, okay, there's our 2. This was the 3% error. Okay, so this would be less of an error. For this D over B, 5 over 5 was 1. Okay, that showed a 12% error. So as that ratio decreases, right, it went from 2 to 1, my error went up. Okay, and if I do a D over B of this, again, D being 2, B being 8, that's a quarter. A D to B ratio of a quarter showed a 100% error. Okay, and so, last year through strength and materials, we used shapes. We calculate shear stress in shapes like this, where our D over B would be 0.425 over 6, right? And that's a ratio of 0.4, or not 0.41, 0.41. So again, if a quarter gives you 100% error, what do you think 0.041 is going to be just as bad? Okay, but this 6 by 4 and a 0.425 is actually the flange of this W 18 by 35. Okay, this is the flange. Boy, I got that bass backwards, don't I? 6.0, 0.425, right? That's the flange dimensions of the W18 by 35. Okay, so that certainly should cast some doubt in your mind as to the accuracy of the FV shear stress, the general shear stress equation of VQ over IB for wide flange shapes. Okay, but if we do plot that, right, if we do that calculation and we did this in CET 243, if we do this calculation, you see that we end up with the solid dark line. Okay, again, if I, we end up with this based on VQ over IB. And what we saw, if we took and calculate shear stress doing V over dt sub W, right, we got the dotted line, right? That's this value. FV is V over dt sub W, okay? So that's really the basis of what we use, okay? And don't forget too, for that shear stress VQ over IT, don't forget using the WT shape, right? We studied how to calculate shear stress at the maximum point here, Q based on a WT shape, right? So we could look up a WT and get its Y bar here, and then calculate YI bar from the neutral axis, okay? And we could, so use a WT shape, okay? So again, it's a lot of review, okay? So now getting into the specification, okay? C sub V1, which means there's also a C sub V2. If I look at what that is back here, all right, if I look at this shape, okay, all right, we see that C sub V1 is, all right, C sub V1, oops, I lost my zoom. All right, C sub V1 is web shear coefficient, right, in here, web shear strength coefficient, and web shear buckling coefficient. So there is a C sub V2, okay? But again, we're going to take a little bit of a simplified, just deal with some simple parts of this specification, okay? A little bit of technical difficulties here. All right, so mainly what we're going to deal with is hot rolled shapes, okay? And notice this H over TW. What's that look like and remind you of? A B over T ratio, okay? So again, we haven't escaped the B over T ratios, and notice the format, it's still a factor, right, times this ratio square root of E over Fy, okay? So if our B over T ratio is less than this product, then we get off the hook a little bit. C sub V1 is 1.0, okay? And you'll find out that majority of our shapes, right? Majority of our shapes meet this criteria, okay? For FY50, okay? So again, we're in pretty good shape. We'll come back and take a look at this stuff, right? Notice H over TW here of less than 1.1 times a ratio versus 2.24 greater than this value, okay? So there's, just like with the thickness cutoffs for compression and bending members, there's width of thickness cutoffs for shear elements, okay? So we'll end up really in a good, nice, easy spot where phi sub V is going to be 1 and omega sub V is 1.5. Again, I remind you of what this is saying. 1.0, that means we're allowing the shear capacity to reach the laboratory capacity, okay, that we're going to use in practice. Okay, it's the first time you've ever seen phi greater than 0.9. Okay, pretty significant. Okay, so we have lots of confidence in the shear strength of our members. Okay, so it really comes down to this 0.6 FY, and I'll remind you again, this is just really the most accurate number is 0.7577 FY, and again, this is the shear yielding shear yield value. Okay, versus, remember, FY is the tensile yield. Okay, tensile yield value. All right, so we're going to take shear stress, shear yielding stress, times my area of my web, D times TW, and then this coefficient for us is going to be 1.0 for all wide flange shapes except those ones that we looked at in the table. Okay, right in here, they're good for all but these shapes. Okay, so we're in pretty good shape with what we have there. Okay, so again, phi sub v is going to vary, but for us, for W shapes, we're going to have phi sub v of 1.0 and omega of 1.5. So technically it varies, but for what we're dealing with, it'll always be 1, it'll always be 1.5. And then I'll also remind you of this table T3-2. And I've referred to this previously, but way over here in the right hand column, there's our values. Okay, so again, if I take a 18 by 35, right, 18 by 35, should have got my H value. All right, 18 by 35, the H value is, or H over TW, again, H over TW, again, that's the compact criteria, just like it did before. All right, that H over TW value is 53.5. Okay, and so let's look at how that compares. Really, again, for FY of 50. All right, let's look at how that compares against our limit, right, of H over TW less than or equal to 2.24 square root of E over FY. Right, so if I take, again, 29,000 divided by 50 and take the square root of that times 2.24, I get 53.9. And again, it's close, but it is less. Okay, so we're good there. So now we can take our V sub n will be, so therefore here C sub V1 is 1.0. So our V sub n is going to be 0.6 times 50 times the depth times the thickness of the web. So 0.6 times 50 is 30 times 17.7 times 0.3, right? And then again, I technically multiply this by 1, which is my C sub V, and I get a V sub n of 159.3 kips, and I know phi is 1.0, so phi V sub n is also 159 kips. Okay, and that's what you see here. All right, and if we take 159 and divide by 1.5, we get 106. Okay, so not too bad compared to where we've been. All right, So wide flange beams, one thing, built up plate girders, different. Okay, still similar, right? We still have a H, all right, and we still have a TW, okay, but you can obviously see the differences in the ratio. Okay, now some other things that come into play is what we refer to as these guys are web stiffeners. Okay, and they help to reinforce a web that's potentially going to buckle. Okay, and that is going to be a function of the clear distance, right, between these stiffeners, and we refer to that as A. Okay, and we have H. Okay, so with A, all right, let's say A and H. Okay, that again complicates things, right? But this is built up plate girder. We're not going to focus on this. I'm just trying to give you an idea. Okay, so for all other eye shapes and members, built up plates, right? Again, H over TW, there's a ratio. Now notice there's this, they slide in this case of V term. In case of V, if you have no stiffeners, case of V is 5.34. If we do have web stiffeners, right, transverse stiffeners, then this case of V is a function of A, the spacing, and H, the depth, right? So again, we're not going to deal with it, but A over H, right, comes into play when we start calculating case of V for plate girders, or, you know, notice here some M shapes. Okay, all right, so again, with the thickness ratio 1.1, less than 1.1, greater than 1.1. Okay, and then it even gets a little more complicated when your clear A to H value is less than 3. Okay, so again, we're going to see H over T as a function of the 1.1, less than, greater than, and then even greater than 1.37. So this is probably a real good synopsis, right? So shear stress or shear strength is a function of B over T ratio, again, times this case of V value, less than 1.1, greater than 1.1, but then less than 1.37, and then finally greater than 1.37. So hopefully that sounds familiar, right? Again, think of our B to T ratios for compact, non-compact, and slender, okay, beam elements, right? That really is what this ends up being, right? So here's these values. So hopefully you see that this is yielding, right? In this zone we got yielding, you know, 0.6 Fy, our shear yielding capacity, shear yielding. In through here, notice the straight line, inelastic buckling, inelastic behavior, shear buckling, or I don't know, just say inelastic buckling. And then in through here, looks very similar to the columns, right? And this is going to be elastic buckling. Okay, again, built-up plate girders are distinctly different. Okay. All right, so I guess that's where we wanted to be. All right, so thankfully we're not getting into these, you know, but just a couple extra terms. I mean, it's not the worst thing you'd have to do. It's just this case of V, and then the dealing with the transverse web stiffeners. Okay. Now, a good old friend that we've talked about before, block shear, okay, does come back into play. Again, if you think of this beam being connected to another beam, we may have to cope, right? This is called a top flange cope. Okay, so you kind of cut off the top flange, really, so this thing can be connected to, you know, another wide flange beam that when you want the top of each to be at the same elevation. Okay, and in that case, right, you can imagine we're going to have, you know, a connection value here, right, that's going to produce block shear, right? Again, shear on this and tension over here. Okay, so again, we're back to our friend block shear from chapter 3. Again, notice 0.6 Fy, shear yielding. Okay, on the gross area. Over here, 0.6 F sub U, shear rupture. Okay, on the net area. And this is based on tension, net tension area, so it's going to be tensile rupture stress. This is based on the net area. Also, well, these are the same, right? These two are the same. It's all based on tensile rupture, not tensile yield. Okay. So again, that's back to this part of the specification. Different chapter, chapter J. So again, you know, often you have to refer to multiple sections in the steel manual. All right. So again, a whole lot of lecture to just say that we have V sub n of 0.6 Fy AW times 1.0, and our phi sub V is 1.0, and our omega sub V is 1.5. Okay, and again, area web is D times TW, but again, and this is C sub V1. I know it's a lot to get to just this little equation, but there's a lot of background that is important for you to understand. All right, so again, let me know if you have any questions.